Okay, this is the start of chapter 9, and I think it's easiest for us to kind of just get it all out there at the beginning. Specifically, I want to talk about what a sequence is, and in general, it's probably not going to feel like something that's totally unfamiliar to you. At its core, a sequence is exactly what I've listed right there. Namely, it's just an informal definition. It's just an infinite list, an infinite ordered list of elements. And you really want to read these things in a particular order. Like this is the first element, this is the second element, this is the third element in the list, this is the fourth element in the list, and so on and so forth. That's important because there are such things as unordered lists of things, right, where you don't really care about a specific order. But a sequence is an ordered list of elements, okay? And that's very important because that allows you, since it's an ordered list, that allows you to think about what happens in the long run. You can say to yourself, well, what if I just kept going in this ordered list? Does something predictable occur? Yeah? Like, do I go somewhere that's predictable? So that's why this thing being an ordered list is important, okay? And the fact that we say, like, for instance, you see this example right here, it says 1, 1/2, 1/3, 1/4, 1/5. Can you predict what the next thing is going to be? A 6th, a 7th, an 8th, a 9th. See, our minds kind of naturally think in this ordered fashion anyways, and we discern patterns, and then we kind of impose it on, a situation like this. So it's sort of natural to think about this as an ordered list. But also the fact that we're saying, that's the first thing, that's the second thing, that's the third thing, that's the fourth thing, that's the fifth thing, etc., tells us how we ought to define this thing formally. Okay? This crazy, weird bolded in that I have listed right here, okay? This guy, that's shorthand for the so-called natural numbers. The natural numbers, okay? And the reason they're called the natural numbers is because they're the ones that arise naturally by starting with the number 1 and adding it to itself over and over and over again. Okay, so if I add 1 to itself, what do I get? 2. What happens if I add 1 again? 3, 4, 5, 6, okay? So the natural numbers are those that you get from adding 1 to itself. So add 1 to itself over and over. Okay, and this little script, boldface looking thing, N, is the notation you use to describe that set of numbers, the natural numbers, okay? So a formal definition for a sequence, because, and by the way, the natural numbers are often referred to, so another way to talk about these, they're often referred to as the counting numbers. Why? Why do you think they're called the counting numbers? Because this is like how you learn to count. 1, 2, 3, 4, etc., right? That's yet another reason why they're natural, is they are the counting numbers, okay? But thinking in this way, thinking of this as an ordered list, makes it so that it's natural to think of the first thing as the first thing, the second thing as the second thing, third thing as the third thing. And so what we're really doing is we're actually creating a function from the natural numbers to our list, okay? From the natural numbers to our list. You're saying, what? A function? Well, the input is what's first, okay? And the output is what? Like if you look at this list right here, okay? Look at this list right here. Oops. This list right here. The input is what's first, and what would be the answer? 1. The input for the next thing is what's second. So the input would be 2. What would the output be? 1/2. Yeah? Well, okay, if the input is 3, what's the output? A third. If the input is 4, what's the output? A fourth, right? So sequence is a function from the natural numbers to this ordered list of things. And so what we would say here is like A1, okay? And we kind of tend to use this notation that I have listed right here. You say A1, that means what's first? And you would say what? 1. A2 is, that means what's second? 1/2. Make sense? A3 is 1/3. And in general, AN, like what's the nth element in this list? Where n is just generic. And what would you say? 1/n. Yes? So oftentimes you end up with a little formula describing the nth term in this sequence. So again, the formal definition, don't get intimidated by this, is that we have a function from the natural numbers. So the input is like which number am I at in this ordered list? Well, if I'm at the 5th number, the output there would be a 5th in this case, right? In this example that we're dealing with right here, okay? But oftentimes you notate these things with like A, and you put like a little sub number on there. You call that a sub-index, okay? And the sub number, the sub-index, that's the input, and A, A sub n is the output of n, okay? So like A sub n is equal to the output arising from input, from the input, which input? N, okay? So A sub n is the output arising from the input n. This is the nth, right? So A sub n is equal to the nth number in the ordered list. Okay, we're just kind of trying to formalize this, okay? So the elements in the list for a sequence, i.e. the elements in the range, so remember range was output, yeah? When you're talking about functions, the range is the set of outputs. What do you call the set of inputs? Remember what we called that for a function? The domain, yes? And that's why we wrote the word domain right here, yes? Okay, so the set of inputs is a domain, and the A sub n's are the range or the outputs. Oftentimes you refer to A sub n as the nth term in the sequence because it's the nth one in the ordered list, okay? And sometimes you use this notation, you put like these little curly braces around A sub n, and it's just understood that, hey, that notation means I'm talking about a sequence here, okay? It's not just one thing, it's like an infinite number of things, A1, A2, A3, A4, A5, etc. Does that make sense? So really, this thing right here is a way of saying, look, I really have A1, A2, A3, A4, etc. And this just goes on forever. And because I get tired of writing these things with commas between them, I just encapsulate the whole thing by putting the curly braces and putting A in there, okay? Just trying to make sure we're on top of the notation here. And oftentimes a sequence is given by a formula, okay? Oftentimes a sequence is given by a formula. Here, I'm gonna erase this stuff here now that I'm moving down the list, okay? So the formula that we had for the sequence above, AN, the nth term was given by 1/n. Does that make sense? AN, the input n, has output 1/n. Yes? Okay. AN equal 2 to the n. What would that sequence look like? So here, I mean, this sequence here, that's easy. That would just be 1, and what would the second thing be? 1/2, a third, a fourth, etc. Okay, what about this guy right here? What would this guy look like? So what would the first thing in this sequence look like? I'm using these curly braces because that's the notation we use for these sequences. What would the first term be? 2? Then what? 4, 8, 16. You see what's happening here, right? It's just multiplying by 2 gets you to the next term in this sequence. What about this guy right here? What about this sequence? What would the first term in the sequence be? The first term means, excuse me, plug in n equal to 1, right? So the first term would be? Okay, yeah, so let me think here. So 2 over negative, so negative 1, is that right? Okay, what would the second term be? Yeah, because it would be 3 over 1, right? Okay, what would the next term be? Yeah, because that would be 4 over 6, which is 2/3. Okay, that's interesting. What's next? So that's the third term. It's 5 over 22, isn't it? Yeah? What's that? The fourth, so hang on, we're doing, oh, right. We're doing the fourth term, right? So the fourth term would be 5 over 13. Yes, thank you. Etc. Okay? But we have a formula even in that weird case. Okay? And finally, I mean, this one's going to get a little strange, you know what I'm saying? But so like the first term in this sequence would just be 1, n to the 1 over 1, it's just 1. And what's the second term? Square root of 2. Third term, cube root of 3. And then the fourth root of 4, which is interesting, yes? Okay? And a lot of times we want to actually compute the limits of these sequences. The limits of these sequences. Okay? So let's do that in these cases. Okay, so watch this. So what if, okay, so let's just kind of look at this. What if I was doing the first one? So an, if an is equal to 1 over n, what is the limit as, okay, what do you think I'm going to ask about? The limit as what? N goes to infinity. Okay, because I want to know about the long range behavior of this sequence. Like what happens if I go on forever? Yeah. Well, the limit is n goes to infinity of an in this case. What is that? I mean, look, we don't, 1 over something massive gets exceedingly close to 0. That was easy. Okay. What about the second thing? So what if an was equal to 2 to the n? Then what would be the limit as n goes to infinity of an? That thing just grows without bound, doesn't it? It just doubles. Every term doubles the previous term. There is no limit to how large this is going to get. So this limit technically doesn't exist, but it doesn't exist in a special way. It's, so what is this? Plus infinity, right? Third, an equal to n plus 1 over n squared minus 3. What's going to be the deal here? So limit as n goes to infinity of an. You guys have done something like this before, haven't you? Incidentally, you could use L'Hopital's rule, because what does the top and bottom both go to? Infinity. So this thing is of the form infinity over infinity, right? Even if you forgot, I'm telling you, you talked about rational functions at some point, didn't you? You said if the degree of the bottom exceeds the degree of the top and the variable goes to infinity, then overall the ratio will go to 0 because the bottom just blows up faster than the top, yes? So you know this limit is 0, but suppose you forgot about that. You say, okay, well, this is of the form infinity over infinity, so what can we apply? L'Hopital, and we say to ourselves, all right, well, this is the limit as n goes to infinity of, you take the derivative of the top and bottom. What's the derivative of n plus 1? The variable is n here, right? What is the derivative of n plus 1? That'd be 1, and on the bottom, what would I have? Yeah, and now it's easy. What's that limit? 0. Okay, so even if you forgot about rational functions and things like that, you would still be able to pull this off. Okay, any questions on that? Because I want to actually turn you loose on the last one, because the last one's sort of weird. Okay. So any questions on those, on what we're talking about here? What a sequence is? It's an ordered list. Formally speaking, it's a function from the counting numbers to the real numbers, right? You have some kind of formula that encapsulates it most of the time. We're interested in things like taking limits of sequences. But any questions on this initial stuff? Well, what about this one? Limit as n goes to infinity of n to the 1 over n. Now, let me ask you, so that's the last one down there. Let me ask you something. What is the form of this thing? Oh. And are those two things in tension? Sure. The bottom is trying to blow up to infinity. The top is saying, excuse me, I would rather you stay at the number 1. The question is, which of those two wins? Yes? Which of those two things dominates the other thing? Okay? So, I think that we've done enough practice with these sorts of things. And in this case, you have a power and a base. Yeah? I think you have enough practice with this sort of thing that you ought to recall something that we did before to handle a situation like this. And I'm not going to say it. I want you to just think about it on your own with your, with people sitting around you. Okay, so think about this for a minute, and we'll come back together in a few minutes and talk about it. All right, what do you got for me? You got 1? Okay, that sounds promising. What did you do to get 1? Yeah, we've played this game before. You said, okay, well, this is the limit as n goes to infinity of e to the natural log of n to the 1 over n. And then what can we do with the power now? Yeah, so this power is going to come down in front of the natural logarithm, yes? Okay, and the limit only applies to what's in the power, remember? Yeah? So that's to our advantage. I can kind of pull the limit into the power. Okay, so this thing is going to be equal to e raised to the limit as n goes to infinity of, 1 over n comes in front of logarithm, which I should probably think of as natural logarithm of n over n, right? And what is the form of that? Yeah, this is actually of the form infinity over infinity, okay? So what can I apply to that limit that happens to be in the power of the exponential? L'Hopital. Okay, I'm gonna write L'Hopital on top of this thing, or LH, just to remind us of what's happening here, okay? And this is going to be e raised to the limit as n goes to infinity of, okay, well, this is curious. What is the derivative of logarithm of n? 1 over n. And what's the derivative of n? Okay, what's that limit go to? 0. So this is going to be e to the 0, which is 1. This, my friends, is a very, very important limit, okay? So this limit that we just computed, that the limit as n goes to infinity of n to the 1 over n, what did we show that this equals? 1. That is a very important limit, okay? And in fact, We actually get for free lots of other things. For instance, what if I would have said, what if I said something like this? What is the limit as n goes to infinity of 2n to the 1 over n? Okay? Of 2n to the 1 over n. Well, what you could do is you could split this up. You could write it as the limit as n goes to infinity of 2 to the 1 over n times what? N to the 1 over n. And then you could take the limit of each one of those things in the product separately, yes? But what does 2 to the 1 over n go to? Think about it. 1. It's going to go to 2 to the 0. Does that make sense? So that part's easy. This is going to go to, like the first thing goes to 2 to the 0. I'll write it as 2 to the 0 times, and we know what n to the 1 over n goes to. That goes to 1. Therefore, the whole thing goes to 1. Yeah? Now, there are other things that we could do. For instance, watch this. Like if I had the limit as n goes to infinity of n to the 2 over n. Okay, do I know this based on that limit downstairs? You do. How? Drake, you're sort of, confidently shaking your head in a yes fashion. So, okay, what would you do? Well, okay, sure, but how could I use this limit down here to give me what I want? You're on the right track.
Well, because you're still basically going to get the same thing, like e limit n infinity of 2 over n over 1 now, and put it still.
Sure. Yeah. So if you went back to what you did down below, you could do the same thing. But also another way you could think of this is like n to the 1 over n raised to what power? Yeah, second. And what does n to the 1 over n go to? 1. So this just goes to 1 squared, which of course is still 1, right? Okay. So what if I had, okay, I mean, there's no stopping us now, right? I mean, what if it would have been n to the 5,000 over n? Who cares? It's just going to be 1 to the 5,000, right? Big deal. It's still, the limit ends up being 1. So this is an extremely versatile, useful limit. Please don't forget it. It will come in handy massively later on, okay? This indeterminate form, n to the 1 over n, limit of n as n goes to infinity of that equaling 1 is a very, very helpful thing, okay? Any questions on that? Any questions on that? Okay, it's good. All right, so I want to go down a little bit here. There are some things here that are fairly basic. For instance, you're already doing some of these things naturally, and this theorem that's in the book is a way of us just kind of affirming you and saying, yes, you are allowed to do that. So for instance, if I add a couple of sequences or subtract a couple of sequences together, and I take their limit, then I can just take the sum or difference of the limits individually. Does that make sense? That's easy enough. And if I have a constant times a sequence, and I want the limit, I can pull the constant out, right? These are things that you already knew about limits working anyways, yeah? Multiplication or division of sequences, right? You can split up the limit across that product or quotient. That works, but of course you don't want to do that if the limit of bn is 0. Okay, there you have to be careful. You guys remember the squeeze theorem? Yeah. Basically, it says in the sequence version of the squeeze theorem, it says that if you have a couple of sequences, an and bn, that both go to the same place, and there is another sequence that's trapped between them term by term, yeah? Remember, these are ordered lists. These sequences are going like this, right? And you have a third sequence that happens to be trapped between them. But those guys went to the same place. So what has to happen to the guy in between? Has to go there as well, right? So if Cn is a sequence that's trapped between An and Bn, and An and Bn both limit to some number L, then the limit of Cn also must be L, okay? And incidentally, that gives you this next theorem about like absolute value sequences. So if you take the limit of the absolute value of the terms of a sequence and you get 0, then guess what? The sequence itself has to be going to 0 also. And the reason that's true is because of the squeeze theorem, because An, of course, is always between minus the absolute value of An and plus the absolute value of An, but the absolute value goes to 0. Does that make sense? So the absolute value we're assuming goes to 0, and therefore the thing in between would be squeezed to 0 also. Here's a little picture of this here it is. Here's a little picture that I have on this in the slideshows here. I was going to show you. So this is kind of the idea behind the squeeze theorem. So the top sequence is 1 over 2 to the n. The bottom sequence is -1 over 2 to the n. And what we're illustrating here is that the sequence -1 to the n over, okay, does anybody know what n exclamation point is? We're going to talk about that in just a minute. That's factorial. That thing happens to be trapped in between those two guys eventually. It doesn't have to be all the terms, but eventually it's trapped between, and therefore -1 to the n over n factorial has to go to the same place that those other two things go to. And both of those go to, what does 1 over 2 to the n and -1 over 2 to the n go to? 0, as n goes to infinity. Therefore, the thing that's trapped in between goes to 0 also. Okay? That's the squeeze theorem. But I wanted to talk about a couple of little examples here, just for our mutual edification. We're not going to go through all of this, but I want to define n factorial. Okay, so this is, by the way, this is said n factorial. N factorial. And what is it? What is this thing? Well, you start at n, and then you multiply that by what? 1 less than that, and then you multiply that by n minus 2, and you keep going until you get to 2, and then 1, and then you stop. Don't go to 0. Excuse me. If you go to 0, it kills everything. Does that make sense? So you stop the minute you get down to 1. So for instance, like what's 1 factorial? That's sort of stupid. What's that? 1. And by the way, for convenience, you actually define 0 factorial to be 1. There's a reason that you do that, and it has to do with with the way that these factorials work later on in probability contexts and whatnot. Okay, what's 2 factorial? Well, that's 2 times 1, right? Which is 2. What about 3 factorial? Well, that's 3 times 2 times 1, which is 6. Okay, 4 factorial. Well, okay, just take 4 times the previous thing. You understand what I'm saying? By the way, 4 factorial is 4 times 3 factorial, right? I'm getting tired of writing all those things out. You understand? 4 factorial is really just 4 times 3 factorial, yeah? And so it's 4 times 6, which is what? Okay, 24. 5 factorial, hey, that's just 5 times 4 factorial, is it not? Yeah? Which is going to be 5 times 24, which is 120, etc. Yeah? So the factorial function grows really fast. In fact, you could go think about this at Chuck's a little bit if you want, but here's a little brain teaser for you. How long do you think it would take for you to count to the number 50 factorial? If, okay, I'm going to give you totally unreasonable things that you're able to do. The number 50 factorial, whatever it is, how long do you think it would take you to count to 50 factorial if you could count? I think I was assuming 10,000 digits a second or something like that. Okay, which of course you can't do that, right? I'd be really impressed if you could, but you can't. Okay, if you could count 10,000 digits a second, how long do you think it would take you to count to 50 factorial? Couple years? 40,000 years? Yeah. I'm pretty sure, I just did this, I was thinking about this computation. I'm pretty sure that if you day and night over 1,000,000 years to count to the number 50 factorial, okay? If you were able to count 10,000 digits a second, so it's a massive, massive number. The factorial function grows incredibly fast, okay? I wanted to turn you loose on these couple of problems that are right here, okay? So calculate 25 factorial over 23 factorial. And then I want you to simplify that weird thing right there, 2n plus 2 factorial over 2n, parentheses, factorial, okay? Simplify those two things. And by the way, the one you do 25 factorial over 23 factorial isn't all that different from that generic thing that I just wrote down right there, okay? So think about those two things and come up with some answers, and we'll discuss it. All right, what do you got?
600.
Okay, so all right, 600. Okay, and the way you got that was basically probably by writing this as 25 factorial. You guys realize that's 25 times 24 times 23 factorial. Right? Then you say, oh yeah, that's just going to keep on going. So then if you divide that by 23 factorial, of course these guys just cancel. Okay? And you get 25 times 24, which is 600. Okay? Now what about this other guy? It's not really all that different. Like you just leave the bottom alone. Okay, 2n plus 2, what's 1 below that? Yeah, 2n plus 2, 2n plus 1, and then 2n factorial. And guess what cancels? The 2n factorial. So you're left with 2n plus 2, 2n plus 1. And I'm telling you, this is going to become important. This ability to manipulate these factorials is going to become important later on when we're dealing with series. Something called the ratio test is going to require us to be pretty on top of our game as it pertains to manipulation of factorials, okay? So it's important to get ahead of this now, okay? Any questions on that? We'll come back and finish up with sequences tomorrow. But now it's time for a quiz.